Okay, here's a recording description of this handout for Unit 3.7 about plucked string instruments. So what kinds of instruments are we talking about? We're talking about the guitar, ukulele, the mandolin, and the banjo, things like that. There are many others from many different cultures. Basically anything with a body and strings. Banjo has a little bit different, so I'm going to erase that for now. And for these things that are like a guitar, ukulele, mandolin, that have strings and a body that has air inside, the excitation is the plucked string. That is what is providing the energy. The oscillator then are the strings. It's important to note that these oscillators are free, meaning they are not driven. The energy is only supplied in an instant during the plucking, and then they just ring until it decays. So they are free damped oscillators. So that's what those strings are. Okay. That means that these instruments do not have a sustain section. Just attack and decay. The band, okay, sorry. The filter or resonator then is the body and the air. Sorry, the body as in the plates, and then also the air inside the body. And then the radiator is the body, the wood, and the air by the air hole. Okay. For the banjo, the up to there is the same, but for the banjo, it actually has a membrane instead of a wooden body that is both the filter resonator and the radiator. For the harpsichord, again, it is plucked strings. The plucking motion is what is doing the exciting, and it's the strings that are doing the oscillating. But for the harpsichord and the harp, the filter or resonator is the soundboard. And then the radiator is also the soundboard. That's the primary source of where the sound we hear is coming from. Okay. So these are modeled for our first approximation as fixed strings. Okay, so the guitar strings are plucked. When a finger is used to pluck, you have a more rounded or gentle bend in the string, which will produce a warmer sound, which means less high frequencies. If you use a pick for plucking, then you get a sharper bend in the string, and it produces a brighter sound. which contains more high frequencies. Okay. So to answer this next one, I need a little more room to draw. So I'm going to come down here to this page. Sincerely hope that gray box didn't mess that up. In case it did, here are the words that I just wrote. Not sure when that other box appeared. Okay, so now let's just think about our modes on a string for a little bit. So I'm going to say here's mode 1 on a string of length L, and then I would have mode 2, and then I would have mode 3, and then I would have mode 4, let's get that a little wrong. Okay. Now for these, I'm going to draw green dashed lines that basically show the equilibrium position. The string was not vibrating. And then remember, when I draw these, that means the string's oscillating between that and this, back and forth, up and down. Okay. Same thing for the other ones, but it's harder for me to draw those. Okay, and so there are nodes at the ends for the fixed strings. And then the other modes, more than mode 1, have these other nodes. Points where that standing wave has a 0, where the string does not move. Okay. Sorry, just need to get a drink. Okay. Now, the idea is that now that we're plucking, it depends on where the string is excited. For example, if the plucking or the bowing, either one, or the striking happens at this location in position down the string, then your spectrum, frequency versus amplitude, if I make evenly spaced lines here for F1, 2, F1, 3, F1, 4, F1, 5, F1, etc., is actually going to be missing mode 3. And mode 6, and mode, that's F3, F6, F9, F12, because if the string is plucked 1/3 the distance from one end, either end, it's plucked at a node, so the plucking position is at a node for F3, F6, F9, F12, or in other words, F3 is 3F1, F6 is 6F1, F9 is 9F1, and F12 would be 12F1. So I'll do another example here. Now, if instead of being plucked 1/3 the distance from one end, it is plucked 1/4 the distance from one end, and you were asked which frequencies would be in the spectrum or absent, well, we'll just say in the spectrum, what would it look like? Okay. All right. Those are opposite things, but I don't know the best way to phrase it right now. So we have our frequency axis, we have our amplitude axis, F1, 2, F1, 3, F1, 4, F1, 5, 6, 7, 8, 9, 10. Okay, pretend those are evenly spaced, where this is F1, this is 4F1, 8F1, 12F1, 16F1. And your spectrum would look something like that. You would have zeros values for all of the multiples of 4. Okay, so it would, the answer to this question would be all harmonics except multiples of 4. Another way to say it is it would be missing the 4th, 8th, 12th, etc. harmonics. Why? Because the plucking motion, the plucking action, happened at a node for those modes. This is a really important thing, and we will see it again as we go on to percussion instruments. The position you play on most percussion instruments, right? Not right in the center on a drum head, towards the end of a bell, like all of those things have everything to do with these mode shapes. And the idea that if you hit in certain places, you won't excite certain of the resonance frequencies. They won't be harmonically related, but there still are resonances because of striking or plucking at a node. Okay. All right, so that one goes with Roman numeral number 2. So let me just indicate that here in case you're looking at for it. Okay, and let's do this question number 1. If the 5th, 10th, and 15th harmonics don't sound, that means they're absent from the spectrogram. Okay, so there's all these other harmonics except maybe those 5th, 10th, and 15th, then that tells you the string was plucked at a node of those, which would occur 1/5 from the end. Right, so that would be if the plucking happened right there, and that was a node. Okay, number 3 is kind of a review from last time, the air, wood, and string resonances. Okay, so let's do number 2. Decreasing the stiffness and decreasing the mass of the top of the plate will have what effect on the air resonance frequency? Now, the important thing to note is that here it's talking about changes to the top plate, and here it's talking about the effect on the air resonance. Okay, and changes in the body, the plates, the wood, those impact or affect the wood resonances. And don't affect it's in the plates. Okay. All right, so now number 3, let's take these one at a time. what is our model? What is our model for this? Okay, we're doing a mass spring model like we had at the beginning, mass M, some stiffness of the spring. The frequency, the natural frequency of that, and thus the resonance frequencies here of our plate, a good approximation, first order, but gives us an idea of how it changes at least, is the stiffness divided by the mass. Okay, so that means that if the stiffness of the top plate or the bottom, either one, if the stiffness of the plate decreases, then from our equation here, you can see the stiffness is on the top. So the frequency, the resonance or the natural frequency, which is what we're talking about here, is directly proportional. So that would mean that the frequency would also go down. If, on the other hand, the mass decreased, maybe it was thinner wood or just lighter weight wood or something like that, then the frequency, the resonance frequency, would increase. Okay, and by frequency here, I mean of the top plate, of the plate resonance, which plate and wood are, wood is the more general term. All right, and just as an aside, what does affect the air resonances? Okay, so those are the air resonances. Think about Helmholtz resonators. AKA, common example of that is blowing across bottles. Okay. You know that a larger volume of air, like a great big jug for apple cider or something, has a lower natural or resonance frequency. And we're talking about air resonances there. So changes in the air don't affect the wood resonances. Changes in the wood don't affect the air resonances. They're two separate phenomena that both work as the filter or resonator for the instrument. Okay. So I talked a little above about this idea of plucked with a finger and not a pick. Okay. So plucked with the finger produces a more rounded bend in the string. Than compared to a pick. Okay. And that will be a warmer sound, mellower sound. And that will correspond to less high frequency partials, or less high frequency energy, which in this part question is worded upper partials. Okay. Whereas with the pick, it's more sharper bend in the string, which has more energy. This idea of inharmonicity.
Thank you for choosing Marriott Hotels.
Sorry. Okay. This idea of inharmonicity is really a separate idea from that question. Okay, separate idea from that question. And this is the idea. Okay, so we have our simple model of fixed strings. Okay. It is a very good model. Okay, so fixed strings. Our model says that it's F1 is V over 2L plus all harmonics. Okay, it is actually a very good representation when the strings, holy cow. Don't know why they're even coming to my iPad. They never do. Okay, very good representation when the string is flexible and lightweight. Okay. As the stiffness and density increase, it is less good of a model. Or the model has limitations. And what those limitations are is that as the stiffness and density increase, okay, the upper partials are slightly inharmonic. Okay. So, for example, if I have frequencies that are 100, 200, 300 hertz, etc., my frequency spectrum, those would be harmonic partials. Most likely created by a bowed string instrument. Okay. But as you go to metal strings on a guitar or metal strings on the piano, the inharmonicity increases. Or as you go to even a sharper and sharper bend on the string that you get, like when you strike, then the inharmonicity increases as well. Okay, so inharmonicity increases. So what does an inharmonic partials look like? What would be our example of that? It would be like 100, 202, 301, 404, 3. I don't know the exact numbers, but the idea is that they're almost integer multiples, but not quite. Okay. And that would in particular be true for anything with metal strings or especially the piano. And that introduces some beating or roughness, which is why the bowed string instruments have the smoothest, most consonant sound, because they have those really spot-on harmonic partials, as opposed to the piano that has a little bit of roughness or twanginess to it, because there are inharmonic partials, which then, are the partialing, and then talk more about it also on the next day. So the idea is what we talked about in Unit 3.1. Unit 3.1, where we were defining musical instrument